Welcome back to Chem 4300. In this video, we're going to continue in Chapter 1, and now we're going to focus our attention on the concept of fields. Now, you may recall, we've already started talking about the concept of fields when we talked about the potential energy. The potential energy is a scalar field, and what we learn from that scalar field is that we can take the gradient of that field, actually the negative gradient of that field, to calculate the force that would be applied to a particle at that particular point in the field. So the gradient would be the derivative along the x, y, and z direction, and then that would form a vector, the negative of which is going to be the direction of which the force that's applied at that point in the field. So what we're going to do now is we're going to take that concept and we're going to go even further, and we're going to look at concepts of fields in electricity and magnetism. And these ideas originate back with Michael Faraday, who's really the pioneer of our sort of modern understanding of electricity and magnetism. And it was he who came up with the concept of the field, which is really, I think, a more fundamental concept that we're going to be working with. So the general idea kind of starts here. For an case of electric field, imagine we have some test charge, which I'll use capital Q for, and we want to know what the force that's acting on that charge due to some other charges that are nearby. So what do we have to calculate? Well, what we have to do, at least from what we know using Coulomb's law, is that we have to calculate, sort of with the superposition of all these forces, the force from charge 1, 2, 3, 4, and 5, and we would do it with this expression here. Now, the way I've written out Coulomb's law, I've taken the charge, which is common for all of these interactions, and brought the capital Q out. And what I have remaining here is something that we're going to define as the electric field. So this definition is how we define the electric field at this point in space due to these nearby charges. But what's important here is that the force that's felt on the charge Q is just calculated by whatever the electric field is at this point. So regardless of what's going on out here, it's always a matter of just knowing what the electric field is here to know what the force that's going to be acting on that charge. So let's take this idea then and look at more detail how we can sort of use this. So one of the ways that people look at electric fields, remember this is a vector field quantity. So the potential energy was a scalar field quantity. This is a vector field. So visualizing this is going to be a little trickier. So what we do is we use these field lines. Field lines have directions, since this is a vector field, so they'll have arrows on them, and they'll start at the sources. And so in this case, the sources will be positive charges, and they'll end at sinks, and so negative charges will be the sinks. The lines will never intersect, and what we'll see is that when the electric field is very strong, these lines will be close to each other, and as the electric field becomes weaker, the lines become further apart from each other. And the electric field at any point in space then is going to be the tangent of one of these lines. So here we see, here's the electric field. At this point right here will be a vector pointing along this direction. Now these lines are all straight, so the tangent is going to be right along the line. But you can see out here, the electric field much further away is also going to be tangent to the line, so along the same line here, but it's going to be much shorter because you can see the spacing between these field lines is less. They're less dense. Here's an example of a physical dipole. So here you see the source and the sink. So the lines are emanating from the source and they're ending on the sink. And we see that the electric field at any point in space is the tangent of the line. So at this point, the tangent of that line is the electric field. Here's another electric field calculated, a tangent of this line, although there's less density of lines here, so that's a smaller electric field. Another example would be two identical charges. If you look at this and compare it to the previous one, you can see the difference with opposite charges versus identical charges. And so that you can see how the lines that diverge here away from each other as we have with the two charges identical. And you can see, again, the calculation which would give you the electric field at those particular points. So it's really kind of tricky to look at these guys and to draw them. I have a really couple nice apps that I discovered by a gentleman named Paul Falstad. I hope I'm pronouncing his name correctly. He's written a number of apps that we're going to use, web apps that we're going to use this semester. And these two I'd like to show you now. I think they really nicely illustrate some of the ideas that we're looking at here. So let me see if I can get my mouse over here and bring this one up. There we go. So this is, in the app, this is a single charge. I'm going to change it to show me just the electric field lines here. So these are the electric field lines of a single charge. I'm going to up the resolution so it looks a little bit better. And I'm going to change, so he has a number of different examples here, and you can see quite a few here. So that was a single charge. This is a double charge. We were looking at that a few seconds ago actually, and you can see the field lines as they're drawn in this example here. Here is a dipole charge. We also looked at that one, and you can see the field lines generated there. But you'll see a number of other really interesting examples. Here's a quadrupole charge. We'll look at concepts of calculating multiple moments of charge distribution. So quadrupole will be something that we'll be looking at later in the course. And this is how the field lines look around a quadrupole. Excuse me. And then we can have things like charged planes. You can see these are planes with charges on them, and you can see how the electric field lines are moving across those guys. Now I also have examples of 3D vector fields. If I go back to my plot here, I'll click on this link here, and this will take us to the 3D vector fields. I'm also going to change this display to be field lines. And here's, again, a point charge, but now we're looking at the point charge in 3D, and you can see it rotating here. And then let's take, again, a double charge, just like before, and you can see now how those field lines are sort of nicely repulsed from each other. You can see as I put the lines there just between them. And so this is a really much cleaner than anything I could have drawn on the screen. And let's go to the dipole charge, and you can see how the dipole charge looks there. So the dipole, you can see the field lines going from the source to the sink, and of course in the point charge example we have only two sources, and so they can't end, so they have to avoid each other in between. Let's go for a line charge. So this is a line of charges, and you can see how the E field emanates out of those guys. So I'm going to leave this for you. There's a whole bunch of examples here. Sort of look through these and help you get a feeling for how these electric field lines will vary with different types of charge arrangements here. So let me go back to slides, and let's move on, and let's look at concept of magnetic field. Now this one is trickier because there is no magnetic monopole, so the analogy of the electric charges we don't have. We have to look at currents. So that makes this kind of a hairy business here, but we can work this out and sort of show you that we have the same kind of relationship where the force that's acting on a loop can be calculated if we know the magnetic field that's at that loop. And the magnetic field is something we can calculate by summing over all the current loops that are generating a magnetic field at this point. So without getting into too much of the details here, you see that, for example, for this loop right here, there's a segment which we call DL2, which has some current flowing in it, and that current is going to generate a magnetic field that will be felt here at this loop, and this segment of this loop here. So if you take this current here and you integrate it around the whole loop, then that's going to generate a contribution to the magnetic field. And then you'll have other contributions from the other loops. So this segment here with its current integrated around its loop for all of the magnet to generate the magnetic field at this point. So imagine you have all these R vectors from here to there, and then you have to work your way around the loop with your R vector changing to this point here to calculate the magnetic field at this point using this integral. It's tricky stuff. Don't worry, we're not going to be going into this kind of detail in the class. But the point is that all of these guys over here will generate a magnetic field at this point, and then there's going to be a force acting on this segment based on the current that's flowing on it and the field that it experiences here. So there's a vector quantity, magnetic field generated here, and then we can, if we integrate around this loop, we can get the entire force on this loop based on the magnetic field in this region. All right. When you're thinking about current flowing and magnetic field generators, there's a simple rule that if you put your thumb along the direction of the current flow and you wrap, this is your right hand, you put the right hand thumb along the current direction, and then your fingers will curl around in the direction of the magnetic field. Now, don't forget that in electricity, that current is a positive flow. So we all know the electrons will flow, when electrons flow one direction, then the positive flow is the other. So the current is the opposite direction of the way the electrons flow. Now, we also know, of course, there's natural magnetism that occurs in matter. And so one of the things we're going to be looking at in this course is how that actually arises. And it's interesting that back in the 1820s that Ampere actually suggested, before he knew about quantum mechanics or anything like that, but he knew about how current loops can generate magnetic fields, he suggested that magnetism that occurs naturally occurs at the microscopic level by microscopic current loops. And it turns out that he's pretty much close to, right on to what actually is happening. And we'll see that as we get into the more quantum description of what's happening with magnetism. And then there are some nice 3D visualization here that Paul Falstad has put together, and I'll run through these too. So this, I'm going to change the display to be field lines here. And this is a current loop. And again, if you take your right hand and you run it along the direction of the thumb along the direction of the current, your fingers will curl with the magnetic field direction. And that's one example he gives. But you can hear, for example, here's a double current line, so two currents flowing and then the magnetic field that they generate. You can look at that. And some other, well, this is just a uniform magnetic field, and that's kind of boring, but let's try here. Here's a current loop. So here's a loop of wire, and that's the magnetic field that's generated around that current loop. So just using that equation that you saw, you could calculate at every point in space, work out what the magnetic field at each point in space from every segment around this current loop contributes to each point in space here. You get some other, here's a pair of loops. Yeah, that's not so exciting. Let's try, this is exciting, I think, a solenoid. So here's a set of concentric current loops that are wrapped around along, I don't know if that's a helix the way he's drawn it there, but you can imagine if you took a rod and you wrapped wire around the rod and you hooked it up to a battery, then you would generate a magnetic field as the current flows through that helix, that coil, and this is the magnetic field that you would generate in that case. Okay, so I'll leave that there for you to spend some time and look at and go back to the lecture. I think we just have one last thing here, is that bringing it all together, then if we imagine like a test charge that's in both an electric and a magnetic field, what is the force that it's going to feel? And it turns out that we need to use what's called Lorentz force law. And of course, there's just the charge times the electric field. We already saw that that's the force it feels. But it will also feel a force by moving in a magnetic field. So if the charge is stationary, then it won't feel any force. But if the charge is moving with the velocity v in a magnetic field, then it would also feel a force, what's given by q times the cross product of the velocity vector with the magnetic field vector. And the interesting thing about this is that this magnetic field will change the trajectory of our charge as it moves through space, but it won't change its speed. So it'll change the direction, but the speed will stay the same, so its kinetic energy will not change. And what we know from the work energy theorem, if the kinetic energy doesn't change, then there's no work done on that particle. So magnetic fields will change the direction of moving charges, but they won't do any work on those particles. And then also I think it's interesting to realize that we've been looking at this so far from a completely Galilean point of view, that there's just one inertial frame. But we know from Einstein that if you move between different inertial frames, what looks like a magnetic field will become an electric field and vice versa. So these electric and magnetic fields will transform between each other as we move between different frames. And that's beyond the scope of this class, but I think it's nice to sort of point that out, that these guys are just manifestations of the same sort of fundamental object, which depends upon which frame you're looking at them in. And actually, there's a couple of nice videos I have here that point some of these issues out. So first of all, this idea of the force of the magnetic field on charges is nicely illustrated in this very old but really well done video on electrons and magnetic fields. So strongly recommend that you watch that guide, check that out. And then this one is a little more humorous, but it's fun because it's a more modern take on sort of explaining how relativistic effects have this exchange between the different frame transformations, and how electric field and magnetic fields are sort of manifestations of the same thing. So we'll leave it at that, and that's the end of this lecture, and that's the end of Chapter 1.